Hello, IB Physics. So in real life, we'd do some little mini labs where we'd really play around a bit with the idea of gravity and the idea of friction. But in distance learning, playing around is a lot harder. So we're going to dive into some notes around how to calculate gravity and how to calculate friction in two different ways, actually. So first off, calculating gravity, if you were in physical science, you've done this before. You might have even done this before in middle school. But gravity is the force gravity, and we think about it in everyday life as your weight. So when you're thinking about how much weight you have or how much weight your iPad has, what you're really thinking about is how much force gravity is pulling that object downwards. And that is equal to the mass of the object measured in kilograms times the acceleration due to gravity of that object. Here on Earth, 9.81 meters per second squared is our acceleration due to gravity. And this means that we get units. So mass is kilograms times meters divided by seconds squared. So we get units that are combined together, kilograms times meters per second squared. And those actually are what newtons are called. So in science, we have these things called derived units, which a newton is a derived unit, and it is made up of other units, other fundamental units, like kilograms, meters, and seconds. Um, so we have our calculation force gravity. What you'll find is that this is actually pretty straightforward. If you know the acceleration due to gravity on whatever planet you're looking on, you just multiply the mass in kilograms by that acceleration. Most problems are going to be set here on Earth, so you'll be using the acceleration due to gravity on Earth, but sometimes it's fun to look and see how things are a little bit different on other planets. So our weight is actually a force, the force of gravity, and your mass is something that it tells you how much stuff you have, how many protons, neutrons, and electrons actually total make you up, and that is your mass. So this is gravity, pretty straightforward. Friction is a little bit more complicated. And it's a little bit more complicated because there's actually two different types of friction. If I push something sitting next to me, so I gently push your iPad with one finger, just like a little poke at your iPad, and notice that if you're just gently poking at it, it doesn't move. And that's because the force you are applying is equal to that frictional force. So that object is not moving. If you keep applying a larger and larger force, eventually, as the force you apply gets larger, eventually the object starts to move, it starts to slide along the surface. And you actually require less force, you apply less force to get it moving. This is a terrible graph, by the way. I have a better graph. This is terrible labels. Anyways, the idea though is that the object is harder to move. It requires more force to get moving if it's not already moving. And I found this nice GIF that kind of illustrates why this is. So when our object is standing still, just sitting on the surface, your iPad's sitting there, all of its sort of bumps and stuff are kind of interacting with the surface's bumps and stuff. They're microscopic. You can't see them with your eyeball, and there might even be some intermolecular forces, but we're not going to get into that. But what we really want to highlight is when it's sitting still, it's harder to get it to move. So it has a larger frictional force. That means that it takes more force for you to get it moving than it does for you to keep it moving with a constant velocity. So here are two ways that you can sort of represent the forces on an object that is moving. And this is missing a force. We can think about it in terms of our free body diagram, which is pretty useful. Our frictional force is pulling backwards from the direction of motion, and our pulling force or pushing force is pushing it forwards. So when the object is moving, this pulling force or pushing force is going to be equal to that frictional force. And this is this kinetic sliding friction idea. And sometimes IB will ask you to label the forces on an object where they occur, which I think is pretty ridiculous. It's not, I don't know. I've never seen it outside of IB. So I think it's a little bit strange. But when we're thinking about that, then the friction is really between the two surfaces. A force gravity is from the center of the object downwards. If they had in this the normal force here, that would be upwards from the surface that the object is on. So, I don't know, only IB does this. I think it's quite strange. But again, our key idea here is that there's two different types of friction. So this first type of friction, this static friction, is you pushing lightly on your iPad does not move because the static frictional force is large enough that it's balancing the force of your finger pushing on your iPad. And so this static friction force can be calculated with a thing called the coefficient of friction. It is a number that doesn't have units. And this is the coefficient of static friction because it has a little s next to it, multiplied by the normal reaction force. So that's just the normal force on the object. And you can usually calculate that in a free body diagram. Since you know the object isn't falling through a surface or flying off it, that means that its weight and normal force are often, not always, but often equal to each other. So this static friction force is a little bit funky looking because it's an inequality. So our static frictional force is going to be less than or equal to the coefficient of static friction times the normal force. And that is because the static friction changes based on how much force is being applied to that object. So if you're just pushing really gently on an object, the static frictional force is going to just be equal to that push. If you have not yet overcome a larger force than the maximum static friction force. So to get an object moving, we need to get a force that is equal to the maximum, actually just a little bit more than the maximum static friction force. And then the object starts sliding. And that's when we get dynamic or kinetic friction. So this is the force of friction dynamic. That means when it's moving. And that is equal to the coefficient of friction of dynamic friction multiplied by our normal force again. So this one is not an inequality, it's just equal to. A little bit more boring, but very, very useful. So if an object is moving and you want to do something with it, calculating its frictional force, this is the equation that you would be using. So anytime we know that an object is moving. And so this coefficient of friction thing, this thing that looks kind of like a U, it's called the Greek letter mu, is something that is empirically measured. It is measured in labs. It is not derived based on our fundamental knowledge. And so whenever you're trying to think about coefficients of friction, you might look it up on a table, like this set of coefficients of friction. You also might be given it or be finding the coefficient of friction in a problem. And so why is the coefficient of static friction always larger than the coefficient of dynamic friction? You notice on the table that is the case. We can see some objects that have a really high coefficient of friction, like rubber on concrete has a high coefficient of friction. And you notice that the kinetic friction is a little bit lower, and that's true of all of these different surface combinations. And that's because of that interaction between the surfaces in this GIF that I'd showed you before. So the maximum static friction is going to always be larger than the kinetic friction. So today you're going to be working on some problems where you'll use these three different equations. You'll use our calculation for our force gravity, you'll use some static and dynamic friction calculations, and as you're going through these problems, when you get to ones that are meatier, probably any ones after the first page I would call meatier, you're going to want to use a free body diagram to set up the problem. I've added a discussion post after this assignment where you can post on problems that you have questions about. And I will check in on that really quickly and try to add in things to help. So if you are like, oh, gee, is this the right free body diagram for this problem? You can make a little discussion post, take a picture of that so that you can get some help on it. And also other people who later on also have that same question can get help on it as well. We will also be working on these problems in class on Thursday the 17th, I believe, and probably a little bit into week 8 as well. because these problems are really meaty. This is the big bulk of this unit where we're going to look at a bunch of situations that are balanced forces, where you are doing some calculations for forces based on a free body diagram of that situation. So good luck, and let me know if you have questions. Drop them in that discussion post. I'll respond to them every day. I'll check out and see what new discussion questions there are. And I also might try to upload some videos there giving some explainers on some of the more challenging problems, because as you get into the medium and spicy problems, they are challenging. You can do them. They just take some time and some effort to try. Good luck, folks. See you in class.